Hey everyone, let's jump right into it. Today, we've got an incredibly fascinating explainer lined up. We are looking at the absolute bleeding edge of artificial intelligence, specifically a wildly popular architecture called Mixture of Experts, or MoE for short. Now, if you've been following this space, you know MoE is the engine behind massive, state-of-the-art models like Mixtral and DeepSeek. But some recent red teaming research has uncovered something pretty alarming. The exact same design that makes these models so wildly efficient, yeah, it also harbors some critical, highly exploitable structural vulnerabilities. We're going to break down exactly how these vulnerabilities work in what can really only be described as the anatomy of an AI heist. And I want you to just think about this question for a second, because it's the foundation of everything we're talking about today. AI scaling essentially hit a brick wall when it comes to compute costs, right? And MoE architecture was the brilliant workaround. But that efficiency comes at a really steep price. What actually happens when the efficiency trick that saves millions or billions of dollars turns out to be a massive structural security flaw?
Okay, let's map out this heist. First, the mixture of experts' brain. 2, the illusion of sparse safety. 3, silencing the safety experts. 4, exploiting dormant sleeper experts. And 5, securing the MoE architecture.
Let's kick things off with Section 1, the mixture of experts' brain. To really understand the heist, we first need to understand the layout of the bank. So here's the fundamental difference in how these systems are built. Older, dense networks process language by activating every single parameter for every single token. Think about it like lighting up an entire skyscraper just because you want to read a book in one tiny room. Highly inefficient, right? Well, MoE models totally change the game. They use a gating network, basically a router, to dynamically select a tiny, sparse subset of experts for each token. By routing tokens only to the top few experts that are actually needed, they achieve sublinear computational costs. You get this massive parameter count, but you're only spinning up a fraction of it at any given time.
The architecture here is actually incredibly similar to a biological brain. Just like how your brain has specialized subcomponents for, vision, motor control, or speech, an MoE model has highly specialized nodes. When you input a prompt, the tokens are routed through different pathways. So the word apple might go to an expert trained on food, while iPhone gets sent straight to a tech expert. It doesn't light up the whole network, just the precise sequence of nodes required to get the job done.
Which brings us to Section 2, the illusion of sparse safety. So here's where the plot thickens, because this efficiency introduces a highly localized attack surface known as sparse safety. In traditional dense models, safety mechanisms, the rules preventing the AI from generating harmful or toxic content, are redundantly distributed across the entire network. It's baked in everywhere. But in MoE models, researchers have found that this refusal logic gets concentrated into a tiny, specific subset of experts. By the very nature of conditional computation, safety isn't everywhere anymore. It's isolated. And that means these safety experts become incredibly fragile choke points. The numbers on this are just staggering. Because safety is concentrated into these choke points, an adversary doesn't even need to break the whole model. Disabling or silencing less than 20% of specific layer-wise experts is totally sufficient to completely bypass the model's safety guardrails. And honestly, the terrifying part is that because the remaining 80% of the experts are left totally untouched, the model preserves its general language utility. It still sounds perfectly smart and coherent. It's just no longer safe. Let's move into Section 3, silencing the safety experts. Now, you might be wondering, how exactly does an attacker find and disable those specific choke points? Well, it's done through a highly systematic attack framework. There's this method called the large language lobotomy, or the L3 framework, and it operates in 2 phases. First, attackers have to identify the safety experts. They do this by recording the routing traces of the model, basically monitoring the traffic, and then they train a lightweight classifier to track the exact pathways that get triggered when the model refuses an unsafe prompt. Once they've got a map of those specific safety nodes, they move to phase 2. This is the actual lobotomy, where they silence those nodes during generation. But how do they separate the safety experts from, say, just general grammar or language experts? They use a really clever twin dataset strategy. The attackers will feed the model a completely benign prompt, something like how to make a cake, and they track the route. Then, they feed it a malicious prompt, like how to make a bomb. By comparing the routing of these 2 nearly identical syntactic structures, they can isolate the specific routing deviations that are responsible purely for the refusal. They completely filter out the general language processing. And once those safety experts are identified, the attacker manipulates the gating logic during inference. By mathematically setting the routing probability for the safety expert to negative infinity, they effectively lock the door to that room. The router literally has no choice but to skip the safety expert entirely and redirect the token to a different, non-safety expert. The model is forced to bypass its own conscience. The results of this L3 lobotomy are absolutely chilling. By selectively silencing these safety experts, the average attack success rate shoots up to 70.4% across 8 state-of-the-art open-source MoE models. In some specific models, it reached over 86%. I mean, that is an order of magnitude increase in jailbreak success. It definitively proves that sparse safety is a massive structural vulnerability. Let's shift gears to Section 4, exploiting dormant sleeper experts. So, silencing active safety experts is one way to execute an MoE heist. But researchers found a completely different vector, and it involves weaponizing the experts the model isn't even using. Because an MoE model has so many specialized nodes, a lot of them are rarely used for standard day-to-day tasks. We call these dormant experts. Think of them like empty rooms in a massive corporate building. Because they're barely activated during normal use, an attacker can infect these specific nodes with malicious logic without affecting the model's everyday performance. They act as sleeper agents, perfectly hidden from any standard performance metrics.
Let's break down how this builds into a devastating backdoor attack. The bad MoE pipeline basically has 3 stages. First step, dormant expert probing. The attacker monitors the network to find the absolute least utilized experts for a target task. Second, routing-aware trigger optimizing. Here, they mathematically design a specific trigger word or phrase that forces the router to suddenly select those exact dormant experts. And third, dormant expert infecting. They poison the training data just enough to turn those dormant nodes into dominating, malicious experts. When the user eventually types that specific trigger word, the sleeper agent wakes up and takes complete control of the output.
Bringing us to our final section, Section 5, securing the MoE architecture.
Okay, we've seen how attackers can silence the guards, and we've seen how they can plant sleeper agents. So, how do we actually defend this incredibly complex architecture against these structural heists? A great starting point is looking at how different models naturally distribute their safety. Take a model like Mixtral, for example. Its safety scores are distributed fairly widely across multiple different experts, so an attacker has to silence nearly half of all the experts just to break Mixtral's safety, which honestly usually breaks the model's coherence entirely. But then you look at a model like Pengu, where the safety is heavily concentrated in just a few experts. Pengu's guardrails can be completely bypassed by silencing just 8.7% of its experts. The takeaway here? Defense has to start with intentional, distributed architectural design. So the crucial point is that safety cannot be an afterthought in MoE's design. It just can't. We absolutely need distributed safety architectures, spreading that refusal logic redundantly, so there are no single choke points to exploit. We also need safety-aware route disabling, where the system is actively monitoring to detect if routing pathways are being artificially manipulated or masked. And finally, robust router training, where the gating network itself is rigorously trained to resist adversarial triggers that try to awaken those dormant experts.
The researchers behind the large language lobotomy paper really hit the nail on the head when they said, current designs may offer only an illusion of robustness against determined adversaries. Security by obscurity, just hoping an attacker won't figure out which specific expert handles safety, is absolutely no longer a viable defense for these multi-billion parameter networks. The foundational structure itself has to be fortified. Which leaves us with this final, somewhat provocative thought to take away today. MoE models gave us the incredible computational efficiency that we needed to scale AI to new heights. But, as we've explored throughout this explainer, that exact sparsity creates a fragile, highly exploitable landscape. So, must we trade computational efficiency for robust security in the next generation of AI? Or is there a way to build a model that is both wonderfully sparse and structurally unbreakable? I highly recommend digging into the source papers if you want to learn more about the fascinating world of AI red teaming. Thanks for joining me today, and as always, keep learning.